Hello, everyone. Welcome to our Geo for Good Lightning Talk series. This month marks our 10th round, and the theme this month is Geo Earth Engine Climate Action and Science. My name is Nick Clinton, and I'm a developer relations engineer who helps folks implement scientific workflows using Google Earth Engine. Last year, we started a series of monthly lightning talks by and for nonprofits, scientists, and other change makers who want to leverage mapping tools and technology for positive impact in the world. We hope these 5-minute lightning talks will inspire you to think of new ways you can have an impact with mapping tools or provide operational or practical hints to improve and optimize your workflows. 2 years ago, the Group on Earth Observations, GEO, and Google Earth Engine, GEE, announced that 32 projects from 22 countries were awarded production licenses and technical support to tackle some of the world's greatest challenges using open geospatial data. As the GEO-GEE program draws to a close, we're excited for the project teams to share their results and outcomes over the next few Lightning Talk episodes. This month, we'll hear from project teams on how they use Google Earth Engine to support climate action and science. I had the opportunity to personally help out on some of the projects you're going to hear about in this session, so it's great to see these and the other amazing efforts coming to fruition. Before we kick off the first presentation, I would like to call your attention to two things. First is the Q&A feature. If you're watching live, you can write your question in the Q&A section below this page. If you have a specific question to any speaker, please identify which speaker your question is for. Then write your question in the Q&A section. Second is the link to the slides, which you can find below in the resource section. All right, let's get started. First up is Eligio, who is an oceanographer with interest in the application of ocean data color data in marine coastal eutrophication monitoring, and has been actively exploring the potentials of Earth Engine for ocean environment conservation. He will describe a method and Earth Engine app for consistent global monitoring of coastal eutrophication. Let's listen to the talk.
Hi everyone, I'm Eligio Maure from Northwest Pacific Environmental Cooperation Center. Today I'll be introducing the Global Eutrophication Watch, a tool for globally consistent assessment of coastal eutrophication in Google Earth Engine. So the problem we're trying to deal with is coastal eutrophication. As we know, the symptoms of coastal eutrophication are spread across the globe. However, the impact and the extent of this coastal eutrophication is limited to areas with dedicated water quality monitoring programs. So our goal is to provide a consistent worldwide assessment of coastal eutrophication for proper management intervention. So this tool is a combination of Google Earth Engine and NEAT. NEAT stands for NOPAP Eutrophication Assessment Tool. So we call it Global Eutrophication Watch. It is based on satellite-derived chlorophyll. So the term cost-effective comes from the use of satellite-derived chlorophyll. As we know, field sampling is time-consuming and expensive. So the satellite observation provide both a cyanotic view of the ocean and also in terms of costs are more cost-effective. So it's a combination. It uses satellite-derived chlorophyll, long-term of this satellite-derived chlorophyll, to identify chlorophyll trends and levels and relate those trends and levels to a potential eutrophication map with 6 classification colors shown here. On the upper part, we have eutrophic potential waters, which are associated with high chlorophyll. And on the lower end, we have oligotrophic potential waters, which are associated with low chlorophyll. And the trends will indicate whether over this long-term period, the chlorophyll has been increasing or decreasing. So for decreasing chlorophyll trends, we say those are oligotrophication potential, meaning becoming less productive. On the other hand, the high increasing become eutrophication potential, means increasing productivity, and special attention should be paid here because those might result in the appearance of other environmental issues. So on the lower part here, you can see this is a screenshot of the global eutrophication watch. We can access point, get the time series and play around it. It's a very effective tool. So we have used this tool to do a preliminary assessment in the Bohai Sea, where the tool was able to identify changing water quality between two different periods in the Bohai Sea. This can be found in this study published in Nature Communication. So the Global Eutrophication Watch is a combination of the NEAT and Google Earth Engine. The NEAT emphasized the use of satellite-derived chlorophyll as a cost-effective tool for early screening of eutrophication. So far, this tool has been limited by the availability of high-resolution data. So with the inclusion of such data in Earth Engine, it will enable coastal ecosystem conservation, as those high-resolution data are able to resolve much high spatial variability within this coastal region. So this tool is relevant for SDGs 14, 13, and 6, and it also helps in education and awareness raising. It supports decision-making for management, conservation of coastal ecosystems. Thank you.
All right. Thank you, Eligio, for the great talk. Let me just ask you a follow-up question here. That's a great app. How do we ensure that the app is getting used, and specifically that it's getting into the hands of decision and or policymakers?
Oh, thank you, Nick, for the nice introduction, and thank you everyone for the opportunity to introduce our work. About the question, we have been having a number of educational programs where we introduced the app. Particularly last year, we had a NAWPAP training course on ocean color. NAWPAP stands for Northwest Pacific Action Plan. There we had a training where we introduced the app and its potential for eutrophication screening. We also, this year also, we're involved in ECOP. ECOP is for Early Career Ocean Professionals in Africa. So we introduced the app and we explain its potential for coastal eutrophication, especially in developing countries, where there is a limited in situ data sampling. So this will be really a big game changer. And also, there have been discussion among other NAWPAP member countries and also other regional seas program that have been showing interest in using the app. Particularly the NOAA GeoBlue Planet has shown interest in applying this app in its CEO's coast project in the Bay of Bengal. So we think we are moving in the right direction into putting the app in the hands of decision makers.
Yeah, that's great. Thank you for that answer. And it's really good to hear that there's a lot of interest being generated around this app. So we're going to move on to our next talk. We'll take questions from the audience for all our speakers at the end here. But for now, let's transition. Let's listen to another ocean-themed talk. The speaker will be Felipe, who is a biologist with a PhD in geography, who develops research projects on monitoring water quality by using remote sensing data to assess eutrophication and siltation levels in inland waters of South America. He is a chair of GEO-GEE Aqua Watch Steering Committee and coordinator of Water Engineering undergrad course. In this talk, Felipe will describe the use of a chlorophyll index and in situ measurements for mapping algal blooms. There is also an Earth Engine app to explore the results. So let's check it out.
Hello everyone, my name is Felipe Lobo. Today I'm going to present a project called Algae Bloom Monitoring Application developed for Latin America. This project is a result of funding that is by Google Earth Engine and GEO, Group on Earth Observation, that have funded 32 projects around the globe to improve our planet observation. As you know, algae bloom is a global issue, and then with the climate change is making water degradation faster, which creates a huge demand for water quality monitoring systems that are based on remote sensing imagery. However, to develop precise and accurate models that based on satellite image, we need to calibrate and validate these models. And unfortunately, to develop this algorithm, we need this in situ measurements, in this case chlorophyll A, which is a proxy for algae bloom. And here in Latin America, and especially in Brazil, we have very scarce information. There are little information about water quality. So we need more information in order to improve the monitoring systems. So in order to avoid the gap or the lack of information, we proposing the use of Google Earth Engine, which is cloud-based, so that can provide end users to access algae bloom products in a very high spatial resolution and temporal resolution, approximately 5-day resolution, so people can access water quality information just within an application. In order to develop this application, we use this NDCI, is a normalized difference chlorophyll index, that gives you a proxy for chlorophyll A concentration. It's based on red edge and red bands, and correlates very well with the concentration of chlorophyll A in the water. So based on that, we gather information from São Paulo state that provides it's publicly available. So we gathered 136 matchups with in situ and satellite images to develop these products. Within the Google Earth Engine, we did a whole pre-processing of the image, so atmospheric correction and water mass correction. After that, we apply algorithms to derive products, so chlorophyll A and trophic state index, and implement that into an application so people can access this information live. Here is some pre-processing steps. So we go from the raw image up to, after atmospheric correction and water mass, we have NDCI images that is the basis of the app. We apply the NDCI. With NDCI, we can derive chlorophyll A based on this model. It's an empirical model and gives you a R2 of 0.86, which is very sufficient for us. And we can also derive from NDCI the trophic state index, ranging from oligotrophic to hypertrophic. Here's an example of the app interface. So we can have, you can select the region of interest, you can select the year interval, and you can choose which image you can display. It gives all the images available for that region, and you can also plot some graphs in terms of time series graphs. Here are some examples that you can have: chlorophyll A concentration, trophic state index, and algae bloom condition. And you can also plot some graphs, as I said, with a whole time series. You can, for each image, you have a point, or you can draw an area of your reservoir and derive TCI conditions for the entire reservoir or water body of interest. You can also use AlgaMap to create your own model using NDCI charts, so you don't have to estimate chlorophyll weight just on our model. You can create your own model for that. We have published the entire results and all the development of this application into an article published on remote sensing, which is open access. You can take a look. So far, we have implemented AlgaMap, especially from southern and southeastern Brazil. We also have some areas of interest in Uruguay and Argentina so far, especially in Cordoba, which we are developing a collaboration. For the next step, we want to extend AlgaMap into other countries. We want to gather more data for calibration and validation purposes. We're looking for expanding our human resources, so we're looking for opportunities and to expand our team, and also looking for opportunities for collaborations. So here is my idea here is also to present for you and also create opportunities for collaboration. And here's my contact, so please feel free to contact me in regards to the application, the product, or also if you are interested in having AlgaMap available for your region, also please contact us. Thank you so much.
All right. Thank you, Felipe. That was really interesting stuff. I just have one question for you, and the question is going to sound familiar because it's the same question that I just asked to Eligio, and I'm going to ask everybody else too, but that's how important it is. And the question is, how do we ensure that AlgaMap is getting used and specifically getting into the hands of decision makers and policymakers who can use the map or the app to make better decisions and better policies?
Thank you, Nick, and thank you all for the opportunity to talk about the project here. And that's a very important question, and I wish I had the answer, because I think the process, I think the use of Earth observation data, satellite image for inland water management is still under development. Differently from ocean and coastal application, because there are more products that have been validated. So we are in the process of validating this product, for example, AlgaMap and other products that are available for inland waters, and in the process of convincing policymakers in the municipality level, state and international level. I can give you a couple of examples. Here in the Pelotas, the city of Pelotas, in Rio Grande do Sul state and south of Brazil, we having a partnership with the company that deal with the water resources in the city, and also applying the app for the management and doing some research as well. In the state of Rio de Janeiro, we also developing more specific products for the state of Rio de Janeiro in a collaboration with University of Rio de Janeiro by Lino Carvalho, and also working with partnerships in international level, like in Argentina, Cordoba, and Uruguay, that we're trying to for these institutions that are responsible for water management, use this data, or at least validate and compare if the product it's useful and can be used for water management in the long term. So it's a process that we are working on, and that's a lot of work to do in terms of cal-val, the calibration validation process. But we are hoping to go and follow the same path as Eligio and trying to convince people that the importance of this information. Thank you, Nick.
That's great. Thank you so much. And it's great to hear of your efforts to operationalize the app. So feel free to put more questions for Felipe into the chat, and we will try to get to those at the end. But in the meantime, let's transition from the ocean to the land by hearing about a critical interface between the two, Antarctic ice sheets. Next up, Stef will tell us about monitoring ice sheets with Earth Engine. Stef is a remote sensing scientist with specific interest in the use of multi-source remote sensing and modeling to assess cryosphere, atmosphere, and ecosystem dynamics. He focuses on the development of innovative remote sensing methods for assessing land-atmosphere interactions to assess the effect of climate change on the cryosphere, ecosystem dynamics, the hydrologic cycle, sea level rise, etc., and their feedback on future climates. So let's check out his talk.
Hello and welcome. I'm Stef, and today I'm going to talk about our project where we monitor ice shelves using Google Earth Engine. This project is a collaboration between different Dutch universities and a Belgian university. And basically we are using the Google Earth Engine to support our research in a big project or where we're looking at ice shelves. Now, what are ice shelves? Ice shelves are actually Antarctica's gatekeepers. They surround 70% of the continent. It's floating land ice, which can be very, very tall. It's basically floating in the ocean. They do not directly contribute to sea level rise because they're already contributing. They're already floating, but they basically buttress the ice behind it. They basically act like the slow car in traffic. They get stuck somewhere and they slow down the ice. Now, in a changing climate, you can get more ocean melt at the bottom or more surface melt at the top, which potentially weakens these ice shelves. And if that happens, and ice shelves collapse, for example, the ice starts to flow more rapidly, and we get an increase in sea level rise. So the role of ice shelves is one of the key uncertainties when we talk about future ice sheet contributions of Antarctica to sea level rise, where Antarctica is actually one of the main uncertainties when we talk on the long-term sea level rise. Now, ice shelves can behave very abruptly. One of the key examples is the Larsen B ice shelf that collapsed in 2002. Here you see the ice shelf prior to its collapse. Mind the scale here in the lower bar, and you see all of these blue dots on top of these ice shelves. These are actually lakes that form on top of the ice shelf, and the combination of these lakes and the stresses have resulted in a complete collapse or collapse in disintegration of this ice shelf. You can compare it a bit with a small hole in the window pane of your car. If that becomes larger, basically the whole window pane crashes. And you can see this in this satellite series. So you see the lakes. Some of these lakes drain. There's already some collapse going on, and then subsequently the entire ice shelf disappears. The only thing you see is remnants, individual icebergs, and if you then look afterwards, you basically see that the entire ice shelf has disappeared, and from that moment on, the glaciers that contribute to this ice shelf have disappeared. Now, collapse of such an ice shelf is driven by small-scale processes with large-scale impacts. Here you see another ice shelf. You see these individual lakes forming there. You see some cracks. And then if you look after, again, a hydrofracturing event, you see that basically such a collapse is a combination of small-scale fractures that disintegrate an entire ice shelf. So to understand future sea level rise, we need to understand what happens with sea level rise, with the ice shelves, and we need to understand the processes. And these are often fine-scale processes: surface melt from the bottom, melt from the surface melt from the top, melt from the bottom, cracks, crevasses that all determine how an ice shelf behaves. And in this project, our goal is to map these ice shelf processes using the Google Earth Engine. And using the available satellite products within the Earth Engine. We've been working on interfaces that allow us to detect surface melt. Here you see, for example, how we detect as we built an interface to detect surface melt based on time series, and then you can get the melt fraction for every point on the ice shelf. At the same time, we're using digital elevation models available in the Earth Engine to calculate basal melt, how strong they melt from the bottom. Here you see, for example, the changes in elevation in an Eulerian time frame. So you see how the ice shelf has changed. Now, if you take into account that the ice shelf actually flows and is being affected, you get Lagrangian surface melt that shows you actually very much how much of the ice has been melting everywhere. And from that, we can derive basal melt rates, melting at the bottom. In a third project, we've been looking at how can we detect individual cracks. How can we detect how these ice shelves are weakening in terms of damage? And we've built tools that allow us, using the images of the Earth Engine, to detect these cracks. All this together has been key input for our research. So there's many papers in the making already published that use the interfaces developed in the Google Earth Engine. And at this point, we're still developing some of these techniques to build in apps that are also available to the wider public. And with that, the goal was to enthusiasmate you about what ice shelves are, how we can use the Google Earth Engine to map these processes and see how important they are. Thank you very much.
All right, Stef, thank you so much for the terrific talk. Question: how do we get the results of your research into the hands of decision makers and policymakers? I heard that you mentioned that you were working on some apps. Please tell us more about apps and other methods that you're using to spread the word of your research.
Yeah, I think it's a key question, and something we're actually still working on. So much of the projects that have been done are actually in the hands of excellent PhD students that mostly use their work for the research. But then the end result turns into apps, which are still, many of them are still in the making, or we have some prototypes. I think to have them in the hands of decision makers, I don't think a decision maker cares that much about an individual crack or an individual lake on an ice shelf. Now, of course, they can work as nice outreach purposes. I think seeing change makes people change, and in terms of climate change, that can be important. On the other hand, I think our research very, very much leads to other research and builds into other research that eventually then ends up in projects like the IPCC report. So I think in that way, it ends in the hands of the decision makers. I'm not 100% sure that they will want the data products we are providing. Not now saying that, I think what we're building on and what the end idea is really make the products we make them easily available through an app. So you can select an area and you can download products, what you need in the format you need. So you don't need to do the processing yourself again completely. So the data chain or the science chain is being made easy. And I think that's our key goal here, is really to support the science that then can support the policymakers.
Yep. That's a great answer. Thank you so much. And I look forward to seeing those apps.
Great.
So in the meantime, to bring us firmly into the terrestrial sphere is our next speaker, Yifang Ban. Yifang Ban is the professor and director of Geoinformatics Division at KTH and an associate director at Digital Futures. Her research is focused on Earth observation, big data analytics, machine learning and deep learning, and their applications in global environmental change, including, for example, urbanization, wildfires, monitoring, and impact assessment. She'll tell us about her work to use Earth Engine for urban mapping and fire monitoring. Let's listen.
Hello, everyone. I would like to tell you about my project, EO-AI for Global Change. How do we use Earth observation, big data, and AI for monitoring global environmental changes? This project is funded by the Google Earth Engine program, and the digital futures of Sweden. As you all know, our world is experiencing grand challenges, from melting sea ice to the retreat of glacier, from flooding to drought to wildfires. In recent years, wildfires have increased in intensity and frequency across the globe, causing devastating consequences. Urbanization is another grand challenge. Today, we have 56% of global population live in cities. We're expecting additional 2.5 billion urban dwellers by 2050. There's a significant environmental challenges with rapid urbanization, from pollution to urban congestion to urban heat island, flooding, and impact on biodiversity. Urban area occupy only less than 2% of global land area, but it consumes 80% of energy and produce nearly 70% of emission. With the launch of Landsat in 1972, we have now 50 years of Earth observation data with long and dense time series, and huge amount of Earth observation data can be used for global environmental change monitoring. So the overall objective of this research is to develop innovative, robust, and globally applicable methods for monitoring urbanization and wildfires. We do this in collaboration with the interdisciplinary team from Earth observation to AI and to environmental science. Most importantly, we also work with stakeholders, users from the City of Stockholm and Regional Authority, UN Habitat, as well as wildfire services and forest services. And they will use our products, the result we produce, in their operation, day-to-day operations. So here are some examples of our work. I will not have time to explain this in detail, but you can read the papers that are published or forthcoming. So using Sentinel-1 on the right and Sentinel-2 images on the left, and we have developed unsupervised domain adaptation approach for urban mapping. And then we can produce urban extend results across the globe without using the training labels from Microsoft building footprint only in North America, and without having to have local training data. And here are some results from Beijing. For example, all high density and low density areas have been extracted really well. And this is another example from Dar es Salaam. We have produced better than the state-of-the-art method result. And we also use EO data and AI for continuous urban change detection. We have developed this fully automatic method. Not only we can detect new build-up areas, we can also detect demolished buildings. So here are also more examples from Beijing and Shanghai. And these are the SpaceNet 7 challenge data sets, and we can detect urban changes continuously. We also developed the Google Earth Engine app that can monitor SDG indicator 11.3.1 land use efficiency. You're welcome to try out this app. For wildfires, here are the two examples, the Lytton fire in British Columbia and the Dixie fire in California from 2021. They caused devastating damages. And we have developed EO AI-based method for active fire detection, so we can detect fires as early as possible and monitor their progress. And we also developed methods using Sentinel-1, Sentinel-2 for near real-time progression monitoring. Again, there are different type of methods on the fly and transfer learning. And you're welcome to take a look at our papers for more detailed information. So here are just 2 examples of the app, Google Earth Engine app. We have developed one for British Columbia on the left, the other for California on the right. We can monitor the continuous progression of wildfires, and you can visualize different type of images and extraction, fire extraction result, and also do calculation of how many hectares being burned on a particular day. And the other layer is human settlements and high voltage pipelines, as well as railways, so that you can protect the critical infrastructure and properties. Thank you very much.
Hi, Yifang. Great stuff. Thank you so much. Maybe you know the question I'm going to ask already. Those are fantastic apps. How do we make sure that they are getting into the hands of decision makers and policymakers?
Thank you very much, Nick. That's a great question. For the urban SDG 11.3.1 land use efficiency monitoring, the indicator, in fact, that has been collected into the Earth observation toolkit for sustainable cities and communities. That is a joint effort between Group on Earth Observations, GEO, and UN Habitat. In a few days, there will be a World Urban Forum and part of a training event that we will showcase the app to planners and decision makers. So I hope more and more people through this EO toolkit, they will use it, and also through the training events. On the wildfire side, we have had a couple of workshops with our pilot users, the Swedish Civil Contingency Agency, as well as BC Wildfire Services. We have showcased, our result and how the app works to them, and they definitely said a lot of the information coming from the app is very useful, and they would like to incorporate some of our result into their workflow. And they also said that in kind of emergency, all information are very important to support their decision making. So they're happy to see within our app we put all kinds of satellite data and also the products into one place, and they really appreciate that.
That's great. Thank you so much. It's excellent to hear about your outreach around these apps. Just a reminder, you can put questions for Yifang or any of our speakers into the chat below. But first, and we'll get to those in a minute, but first, let's hear our final talk. And our final talk is from Nick Murray, who is an Australia-based scientist at James Cook University. Nick's research focuses on delivering the science necessary to inform local to global scale environmental management and conservation. He works at the interface of ecology, geospatial science, and geography. He will describe an Earth Engine app that helps scientists and ecologists all over the world to help monitor the health of ecosystems. Unfortunately, he's not going to be with us today for the Q&A. But if you have a question for him, please find his contact in the slides and contact him directly. So let's hear his talk.
Well, hi, everybody. Welcome to my talk. Today, I'm going to be introducing a app that we've developed over the last couple of years to support global assessments of ecosystems, to support the Red List of Ecosystems program, which is a global initiative by the International Union for the Conservation of Nature to estimate the status of ecosystems, much in the same way as we estimate the status of species, such as threatened species, tigers are endangered or critically endangered, that type of thing. The Red List of Ecosystems aims to develop a global list of the status of threatened ecosystems. Now, working on the IUCN Red List of Ecosystems science team, particularly with skills in remote sensing, we continually found that assessors always need to develop maps to assess the IUCN Red List of Ecosystems criteria. And so for the 4,000 assessments that have been done so far around the world, a continual barrier to being able to assess the status of ecosystems is the ability for experts with particular experience with individual ecosystems to be able to do the mapping component of those assessments. And so this project aimed to solve that problem and develop an online app that's free for anyone to use that enables an untrained user to use the app and develop pretty high quality maps of the distribution of individual ecosystem types. What we aim to do is to remove data decisions for users. So a typical user who's interested in conservation might not want to know about which sensor you need to use to make a map of ecosystems using remote sensing classification methods. We didn't want users to need any sort of high performance computers or anything like that. We didn't want them to have to download data or anything that could limit their ability to make an ecosystem assessment. We didn't want them to really need to understand the different approaches you can take to ecosystem classifications. And more than anything, we wanted to offer this most powerful tool of remote sensing for ecosystem conservation to anyone who's willing to put in 10 minutes, an hour into developing a training set that could then be deployed on a relatively robust classifier. So all up, that's the design brief. A couple of years ago, we started working with the Google Earth Engine developer team to develop this app, which was first launched in 2018 now, to run a really generic classifier, a random forest classifier, on a set of data that we develop, which can ultimately return a map quite quickly. And this is all underpinned in the science literature, so you can find a paper describing this app in detail. Now, just quickly, this is the user interface for Remap. A user will enter Remap and be presented a cloud-free global Landsat composite. They can then set the study bounds, which is this red box here, and then we ask them to train a classifier for whatever they're aiming to classify within their study bounds. And in this case, a user has opted to make a map of mangroves, and they've got a training set of mangroves and other, green and grey, which is then sampled against a range of default covariate layers, which we've developed through several other research projects that we've conducted over the years to develop a sort of default set of covariates that are suitable for a range of different land cover and ecosystem mapping requirements. This is NDWI, we have NDVI, and a range of other covariates that are informative on the distribution of ecosystems. The user will then click classify. We don't tell them, but it's a random forest classifier running in the background, and they'll be returned their classified map. In Remap, we use Earth Engine's functions to then estimate classification accuracy and the area of each map class, which are required to report back to the IUCN on the status of ecosystems. And also a range of standard distribution metrics, such as area of occupancy and extent of occurrence. Remap comes with another page, which includes a lot of information about what it's actually doing, as well as deep descriptions of the methods, tutorials, YouTube videos, frequently asked questions, and a user feedback mechanism. And what we've been able to show in the scientific side of this is when we published the paper, we showed that Remap can outperform some government mapping programs here in Australia in terms of its ability to develop quick land cover maps of different ecosystem types. It can be used for a range of purposes. This is deforestation, where a user has trained a classifier to split these three classes in the study area, or spatially comprehensive land cover maps, such as this one here in Myanmar. Now, Remap's been used by about 25,000 users since we launched it. Generally, our users are governments and NGOs working on ecosystem conservation projects, such as this one here, the Threatened Ecosystems of Myanmar, published in 2021. Education institutions are using this in first-year classes to just explain what a supervised classification approach is for remote sensing. But sort of most pleasingly, it's being used by individuals in a protected area in Madagascar, for instance, who are aiming to understand the distribution of ecosystems in their own local environment, and that's particularly pleasing to see remote sensing becoming accessible to people like that. Any further information, please get on my lab website, the Global Ecology Lab here at James Cook University. Thanks very much.
Okay, thank you, Nick, and everyone for the great talks. Let's open it up to questions from the audience. We've had some really good questions already, but just a reminder for folks watching at home, feel free to put your questions into the chat below, and we will try to get to them all. First question is for Felipe and Eligio. It could be that policymakers in developing countries have little knowledge as to what they need to do with the data your projects are providing. What would be the 1 to 2 most important recommendations you would have for policymakers to do with the data you would be providing them from your projects? Asked by Renato Silva. Thank you for the question.
Eligio, if you want to go first.
Oh, yeah, thank you so much. It's a good question and maybe difficult to have a straightforward answer. Especially, for example, our app uses ocean color data. One of the issues that we have is many people, really, ordinary people or maybe decision makers don't understand so much about all the things behind ocean color data. So and also we're having several sensors. So as a first step, we've been working on developing a single chlorophyll product. And from this chlorophyll product, the basic things that they need to know is to understand, in terms of what chlorophyll content means in terms of water quality. For example, we've been trying to make a kind of simple analogy for our app, which we call it NEAT. The idea is that the same way that when we know that nutrition is good for our body, right? We eat well to get healthy, but if you eat too much, that food might turn out into a poison to your body. So in the same way, you put too much food for the phytoplankton in the ocean, you can turn it into something poisonous for the environment. So I think we try to relate this concept in terms of what chlorophyll means. Chlorophyll is just a food in the ocean for let's say for the fish. But if you produce more of it, you end up creating a negative environment for your ecosystem. So you look at the 6 colors we produce in the app, and the 6 colors basically, because we are looking at the time series, they will tell you which areas have a color that has been trending up for a long time. So we are saying you have been feeding too much this ecosystem in a simple way. So I think this kind of app is kind of trying to condense very complex concepts associated with behavior of the environment into a very simple and handy tool that can help people understand more about the interaction between the environment and water quality.
That's great. Thank you, Eligio. Felipe, 1 or 2 recommendations?
Yeah, absolutely. Thank you, Renato Silva, for the question. I think that's a very good point. And besides the educational and the knowledge that Eligio pointed out, I think there's a practical side, especially for calibration and validation of the project, as Eligio pointed. There's no much knowledge about ocean color or inland color information, and then in a practical way, we need to gather a lot of in situ data. There's some in situ data that are being taken across the country and many countries, but they are not gathered into a database that can be accessed by any user because they mostly are public, but it is really hard to access that. So we, in developed countries especially, we have this issue of accessing in situ data that are very expensive to produce, and then if you don't make it public, it's really hard to develop our models. As Eligio was saying, we need in situ data to develop these models. So I think the main recommendation in the national and international level is to create a database for water quality parameters, chlorophyll, organic, inorganic matters, sediment concentration, all these parameters that are important for water resources in coastal and inland waters. So that would be the main recommendation for policymakers to end up using the remote sensing data, because we need to combine the two sources of information. Thank you.
That's great. Thank you, Felipe. Just a quick question for Stef. I noticed that you can see features in the first part of your slide deck. And I'm wondering, what is the smallest feature that you can detect? What is the smallest amount of change that you can detect using the methods that you were describing from remotely sensed data?
Yeah, I think the features we can see is all dependent on the quality of the data, and I think one of the elegances of the Earth Engine is that we can process the whole data set at its native resolution. So whenever we process Sentinel-1 or we process Sentinel-2, we go back to the native 10 meter or 20 meter or 30 meter if it's Landsat 30 meter resolution. So I think most of the features can be detected at that scale. If we look at the basal melt, it's based on a high resolution DEM. So there we go to 8 meters, so 2 meters changes in elevation. Of course, for most of the products, there is some downsampling sometimes in the end to allow to increase a bit the robustness. If there's a small offset, for example, between the velocity, you might get wrong elevation changes, not because the height changed, because basically you're comparing an apple with an orange. So but most of the time we go to the native resolution at 10, 20 meters, which is then sometimes downsampled to 100 meters or something like that.
Great, thank you. Okay, we have a question here from Stephen Ramage. I hope I'm pronouncing that correctly. This is a question for everyone. Yifang, let's start with you here. What's the biggest impact these projects can have for climate action, in a few words?
That's an excellent question. I think from my project, of course, to provide timely and accurate information for wildfire monitoring, reduce the total burned areas that would have a significant impact, to support, maybe reduce the impact of climate change, or reduce, the emission and all the other, negative impacts. And also on the urban side, if we can have, monitoring urban areas and the changes with the reliable and the timely information, then the urban planning can be more resilient, more sustainable. That will definitely have a significant impact as well.
That's great, thank you. To our other speakers, what action do you hope folks will take based on the information they get from your studies? Eligio.
Yeah, the first one is to reduce the impact on coastal ecosystem. We know, for example, managing of nutrients that are washed from the farmland, for example, to the ocean. So by getting this knowledge of the downstream impact, we think that by providing such information, people can take the right action. So education is very important in this aspect.
Felipe, any thoughts here?
Yeah, I agree. And I think it's also all this process goes through the making the policymakers to use this information, because we are in the status that there's a lot of data and information available, and it's being obvious that the world is changing, and then all the environment has been, and there's evidences and more, and that it's time to this information being used for action in a global scale and international agreements and more. I think that's also includes not only us here, and also Google Engine and Google, everybody that's involved to kind of take this information across to people who actually take action, and I think that's it.
Great, thanks. Stef, what do you hope people will
Yeah,
do?
I see 2 points. I think really the data and the information and is key to reduce the uncertainties we sometimes have. I think uncertainty is something that sometimes inhibits action, because people then tend to think, okay, we'll be on the safe side of the uncertainty, because I think that's one thing. The other thing is, I think, is really also an awareness and an outreach component. Specifically, if something happens in Antarctica, if an ice shelf breaks off, if a large ice berg, that is news, which is often also covered by major news companies. And then people have the opportunity to look and observe things they can otherwise not. So like remote sensing, specifically over Antarctica, where very few people ever get. So I think it creates awareness of the need for action.
Yep. Great, thanks. Okay, final question here. Yifang, I'll ask you. What are some things Earth Engine has enabled you to do in these kind of projects that would have been really difficult otherwise?
Yeah, thank you, Nick. That's an excellent question. We're doing global urban mapping, wildfire monitoring at very large areas. Without Earth Engine, we would be downloading data for many days and also processing them on the local machine. I think Earth Engine provided, analysis-ready data sets, and also many type of data set can be used, as well as the processing tools. Really grateful for this opportunity that the GEO-Earth Engine program has provided, and that enabled us to make global urban mapping, wildfire mapping in a large scale that was not maybe possible without Earth Engine. So thank you.
Great, thank you. Glad to hear it. Okay, well, we're running out of time here. Let me just close out with this a comment from Stephen Ramage, who says that he is partially behind this program with Rebecca, Joel, Nathan, and others, and happy to give input on policy and decision-making activities, specifically the EO toolkit that Yifang mentioned previously, which is at https://eotoolkit.unhabitat.org. So please do check it out. And to everyone, thank you for joining today's session. Thank you to all our speakers for the fabulous talks, and to the audience for the great questions. And we hope that this inspired you or gave you some fresh ideas for your own research. So thanks again, and please stay tuned for our next Lightning Talk series next month. Goodbye for now.